Welcome and thanks for joining us. My guest today is Ben Cushing. He's the chief architect for health and life sciences at Red Hat. Ben, good to have you with us.
Great to be here.
And recent developments have shown around the world, let's say, that you don't necessarily need for the artificial intelligence great journey the sophisticated hardware people thought we needed. Red Hat has known this for some time, though, haven't you?
That's right. For at least the last 2 years, Red Hat's been working towards creating small language models that are not dependent on expensive hardware for both the inference and training.
And is the fact that they're small language, meaning they are small in terms of the intensity of compute that they need?
That's right. So the amount of parameters that make up the model is significantly diminished. Um, the Granite family of models that we work with are anywhere from below a billion to, I think the largest is probably 32 billion parameters, which is still significantly smaller than the type of large language models that you see in the news cycles.
So then people could experiment with these small language models and train them in their own environments or on a smaller test bed than they would need with a large language model as they're understood in the public domain out there.
That's right. And in some cases, I've seen evidence of people doing this sort of training on their local machine, like their laptop.
Wow. Well, what is a small language model in relation to a large language model? And get us to some of the use cases, for federal agencies, especially those in the health area.
Well, besides the differences in the parameters, just the sheer amount of information that's understood and housed within the model, I think what we're talking about here is domain specificity. So, an example of that might be if you needed a small language model to know just enough about a particular type of data object. So like, maybe you've defined a, actually let me back up a second here. So let's say for instance you have a large language model that's going to be producing some sort of output. That output might be a medication. Okay, and that medication might be getting entered into an electronic health record. Um, there's uh, there's really no step in there for the validation of that output for its entry into the electronic health record, besides the electronic health record actually accepting it. In this case, a small domain model, which knows a lot about just the medication object itself, would be sufficient to judge whether that object is sufficient and well formed and can be inputted in or yeah, can be submitted to the electronic health record. So in this case, you have, again, a model that only knows a certain amount. It's incredibly efficient and is now if you imagine like thousands of these little tiny worker models, they're able to create a collective capability that surpasses the large language model itself because each one is so good at its particular task.
Right. So, in other words, if I am, say, doing research or I'm doing a clinical trial, just to make this up, of a particular drug, which nowadays is particular molecules, I would not need to throw the entire library of all known drugs into a language model to research that one molecule or that one formulation. In fact, that would be a negative result versus knowing everything about that specific thing in much more depth
Well,
than the LLM could do.
I'll give you an even more extreme example. So, like, if you're studying, let's say, a particular small molecule that you're evaluating for some sort of form of efficacy for a disease state, you don't need the model that's doing that work to also know lots about automobiles, right? A large language model knows a lot. It doesn't, but we don't need all that knowledge when we're trying to hyper focus on this particular domain. So the idea is that we can get way more knowledgeable within a certain domain by pruning out a lot of the extra noise that's actually not relevant. Now, there's definitely use cases where the large language model is really, really helpful. Language, for instance, is one of those things, like where, human beings, we have, a whole mosaic of thoughts going through our brain that add context to how we speak. That's a really good example for a large language model. But when it comes to actual domain knowledge, the retrieval of that knowledge, and then the surfacing of that knowledge within a certain context, domain expertise is much more valuable. And in order to get to domain expertise, we have to be able to prune away all the extra stuff. And that's actually a lot of ways of the way the human brain works, right? As we as individuals become experts in a specific field, kind of lose a lot of the stuff we used to know, right? Even our muscle memory starts to fall away. So what you're seeing is sort of that realization that the large language models won't just become these omnipotent things that know everything. More so, we're going to get more and more hyper focal focused cognitive agents that are then connected to each other, and then you use a form of routing of requests. So if I ask a particular question, that question will inevitably lead me to the right large language model or small language model, depending on the question, which can then answer it with the level of specificity that I require for the question.
Got it. And you call this domain alignment.
Yeah, actually, I don't call it that, but that's a really good way to call it. Thank you. I'm going to use that.
All right, good.
Good.
No charge. And
Yeah. Mhm.
well, let's talk about Red Hat in this context a little bit, and especially the architecture of the way a lot of agencies are going about their journeys with their data and their language models, whether large or small. And that is they tend to look toward the cloud as
Mhm.
the repository of where the models live and do their work and where the processing is, the hyperscalers. And yet you're finding that that's not necessarily the only place you want to be or even can be.
It would seem we've reached a bit of a plateau on cloud adoption. The cost uh, has sort of shifted. There's actually quite a few agencies that are pulling back from cloud adoption, only because they went full steam ahead on moving everything from applications to data to operations, but didn't really do any sort of cost containment. And so, for any service, it's really easy to turn on and get working right away, which is a good thing, by the way. The challenge with that is it because it's so simple, people don't spend enough time analyzing what it might cost in the back end. So their cloud costs are pretty much every year ballooning across all the agencies, and that it's not something they can sustain. So there's a focus right now on evaluating the capital expenditures that have already occurred. So that they've spent a lot of money on these on-prem data centers, which are still they're looking a lot better now because they already understand that those costs, those are sunk costs, right? So really the costs at that point are what's the electricity, what's the cooling, as opposed to the hardware. How can we get more from what we already have? And this is where those uh, domain aligned models really come into play because we can bring them into these environments where you may not have the best hardware, but you can still achieve your mission and still make a dramatic impact.
And most agencies generate their data locally, so it might make sense to keep it locally, and then you
Mhm.
avoid all those cloud transfer back and forth costs.
Yeah, and even going further, like outside the data center, I think that's absolutely true when it comes to sensors, right? Like example of this would be USGS and their water mission. I mean, they have sensors in lakes and streams all across the United States, right? There's something like I want to say like 10,000 relay stations across the United States. What's stopping us from having models that are training and tuning and also doing inference at those stations? Right? The only thing stopping that from happening is the realization and the management of that fleet of models. And so this idea of domain alignment would give us that sort of future. And it would actually be done for a whole lot less money because there's less data moving over the network. So the network doesn't have to be as powerful. A lot of the existing modalities are useful. The hardware that already exists at those edge locations might be good enough to actually do the inference we need with the models as they're deployed to those edge locations. So, and I say if because we wouldn't actually know until like you go in and do the cost analysis and everything else. But the physics of it, at least, point to it, the tremendous cost savings.
So with AI at the edge and maybe redeployment of some of these modelings and processing in your own data centers, what does the cloud then do best for an agency? Because they still have those contracts.
I think that the cloud is still very viable, but it usually acts as a more of a centralized location for where you actually bring a lot of the other inputs in. So like the cloud, I think will always really excel at doing trend analysis, any sort of long-term time series analysis, anything like that, because that's where you'd actually have sort of the longitudinal view of all your data all at once. The cloud can scale for that. Um, and you don't necessarily have to bring all the data into the cloud for that as well, right? There's data federation strategies, which would allow you to uh, essentially the cloud access would be to the on-prem, and you're essentially queuing up and caching the data you need into the cloud for the analysis itself. And then once you've done that work centrally, the data can be treated as ephemeral and released. And that's actually another good way to save a lot of money because uh, one of the higher costs in the cloud is egress costs, right? Taking data from one cloud into another or data out of the cloud is what's really expensive. So in this case, what I'm describing is inbound data into a cloud environment, doing analysis on that, providing trends, making decisions, and then forgetting the data or caching it for a few further analysis.
So the takeaways then are think in terms of smaller domains, smaller models, doing what you can at the edge and keeping it local to the extent possible. And you'll get better results, faster results, and save some money.
Exactly. That's right. Do more with less.
All right, that'll ring true, I think, in today's government. Let's thank you for being with us today. Ben Cushing is the chief architect for health and life sciences at Red Hat. Thanks so much.
Thanks, Tom.
And I'm Federal Drive host Tom Temin. You're watching Federal News Network. Let's go back to the studio now for more on our AI and data exchange.